Welcome everybody to the sixth and last session of our seminar series on theories of consciousness. Today we have the pleasure to have with us Matteo Grasso, who I should add is a friend and was also a bit of a mentor for me when I was in Wisconsin. And Matteo will give a talk on integrated information theory, which we already heard a bit about throughout the series. And Matteo is a scientist based at the University of Wisconsin-Madison. He completed a PhD in philosophy at the Roma Tre University. And after that, he worked as a postdoc at the University of Oxford, doing research on powers ontology and the metaphysics of consciousness. In 2018, he joined Giulio Tononi's lab, and he contributed to the development of integrated information theory. His research spans across philosophy and computational neuroscience and focuses on improving the formalism and theoretical underpinning of integrated information theory, exploring its metaphysical foundation, implication, and applying IIT, in particular to the study of the qualitative component or content of subjective experience. His focus at the moment are the extendedness of space, the feeling of flow of time, and the experience of objects as a particular instances of a general concept. With that, welcome Matteo, and I'll hand it to you.
Thank you, Francesco. I'll share my screen. Okay. Does it look good on your end? You can see my screen?
Looks great.
Thank you. Okay, welcome everybody. First of all, it's a pleasure to be here. I think this series in particular is amazing. I would like to thank Francesco and Alex for the invitation, and also Eleanor and Chiara, everybody else from the organization that I haven't interacted with who facilitated the whole event. I think there was a great lineup of speakers and a very engaging audience so far. So I'm really, grateful to be here talking with you. So I would like to talk about integrated information theory. You probably heard about IIT in the past, and I think Francesco did a fantastic job in introducing also the main tenets of IIT, but also contextualizing IIT in the general field of consciousness science. I appreciated also other references, for instance, in Liad Mudrik's talk and Johannes Kleiner's talk to IIT, which makes my job here much, much easier. So thanks for all that. So first of all, I would like to provide just a little bit of context and really share something that is more of a personal feeling. I am also really grateful of the fact that we are able to talk about consciousness. We have right now 41 people here gathered, and we are able to talk about science and philosophy of consciousness with amazing technology, but also with amazing track record of studies and theories and proposals. Like Johannes pointed out, there are proliferation of theories, which can be seen as a bad thing because there is a lot of competition, and sometimes there's a little bit of a bad blood maybe between theories, but it is also exciting and amazing because it means that a lot of people are working on this topic, which arguably is one of the most important ones. And just to start on an optimistic note, I would like to remind everybody of also the fact that there is competition between theories, but there is also convergence. And there's many papers that point this out, but one paper that struck me as particularly clear and interesting and engaging is this paper titled Consciousness and Complexity, a Consilience of Evidence, that came out in 2021, where Simone Sarasso and Marcello Massimini's lab members did a very good job in gathering all the evidence throughout the literature of the variety of studies and proposals in consciousness science. And they tried to highlight really the convergence, meaning the overlap, the common denominator in all these theories that really point at, roughly speaking, some form of complexity related measure that seems to be working very well across many different conditions, such as sleep, anesthesia, hallucinatory states, coma, disorders of consciousness. And there has been now hundreds of publications and a series of a build-up of evidence that really spans possibly 20 years. So we're actually kind of in good shape. We are making progress, even though we might still need a revolution, but at least there is some, results are showing if you are able to look between, the big heap of fantastic research. So this is an optimistic note. And in the midst of all this, you've heard about a lot of theories so far. I am going to talk about one theory in particular, which is IIT. And IIT tries to provide maybe one contribution that it is admittedly particularly ambitious, but it really tries to explore one way to answer some very hard questions. And I want to preface my presentation by saying that IIT is likely incomplete. It is likely provisional and superficial in some senses, but there is solid results already that indicate that perhaps this is a direction that is worth exploring. So I'm going to present some of these results after giving you a very short introduction of IIT. So just to convey how rich the literature, not only in consciousness science is, but also in particular on IIT specifically, I invite you to go on our website, which is the Center for Sleep and Consciousness on the Psychiatry Department page of UW-Madison. And we have two tabs around research and theory, one that lists all the publications that are related to IIT. You have more than 150 papers that somehow tangentially refer IIT, published by members of the lab. And then we also have a shorter list or an overview of the main papers of IIT. As you possibly have heard, IIT changed a lot through time. And that's, in my opinion, it's a good thing. We tried to present IIT in versions. So we had a 1.0 version that goes back to 2004, and then a 2.0, 3.0 version. And then in 2023, we actually published the 4.0 version of IIT, which we consider being possibly the first mature version of the theory. So if you're interested in digging a little bit more in IIT, I recommend to read at least the foundational papers, 1.0, 2.0, 3.0, 4.0, and then a lot of satellite papers that clarify philosophical foundations, implications, etc. Okay, so in the context of IIT, IIT is a theory of consciousness, and like we said, many people pointed this out. First of all, we have to clarify what we mean by consciousness, and also what the explanandum of the theory is. What are we trying to explain? What are we trying to address? I would like to stress that for IIT, consciousness is experience. It's subjective experience, is what it feels like to be a human being, or any conscious being, really. It is what it is like to be you when you wake up in the morning, open your eyes, and suddenly you're back. Maybe you were dreaming and you were there in a different world, or maybe there was just nothing going on, right? So that thing that appears in the morning, that's what we want to explain. That's consciousness. What we do not mean by consciousness is all the accompanying functions, the neural processes, the correlates, the activity in the brain, the behaviors that come with consciousness. These are important tools, and we ought to use these tools to maybe explain consciousness, but they are part of the explanants. They are part of what we use to explain consciousness, not what we are trying to explain. And again, consciousness might have a function, but we would like to have a way to study consciousness per se before studying its functions, which is another very interesting problem. I would like to point everybody to this fantastic paper that I co-authored with Francesco Elia and other people from the Tononi Lab and other places, called Consciousness and the Fallacy of Misplaced Objectivity, where we really try to clarify what we mean by consciousness within IIT, and also make the case that what we want to explain is really this subjective experience, and we want to explain it with objective means. So we don't want to commit this substitution fallacy that Francesco was pointing out. Yes, I can provide the links later. Somebody send in the chat. So we would like to explain when we have an experience of something in the outside world or in our inner world, we would like to explain what it is like to experience what we are experiencing. And we would like to do so by referring to some objective measurable property. So in particular, IIT claims that there are two questions that we should try to address. For basically every scientific theory of consciousness should really try to address at least these two questions. So the first one is, why do specific regions of patterns of activity in the brain matter for consciousness? So what is the substrate of consciousness? This comes with a series of related questions. So for instance, why the cortex seems to be very important for consciousness, whereas like the cerebellum seems to be less important for consciousness. So we can remove, literally physically ablate the cerebellum. We have a lot of impairments in movements and motor coordination, but consciousness seems to be unaltered, despite the fact that the cerebellum contains 70 billion neurons and the cortex only 16 billion neurons. So it's really not just a matter of numbers. We would also like to know, with a theory of consciousness, what changes in the brain between wake and dreaming, between dreamless sleep and anesthesia, and ultimately between consciousness and unconsciousness, or high consciousness and low consciousness. We would also like to know whether the most important units for the substrate of consciousness are neurons or mini columns or microtubules. A theory should say why it seems like the activity of neurons and not molecules is important for consciousness. And then finally, just to wrap it up, this theory should really allow us to say whether a person in front of us or a system of any sort, a being, is conscious or not. We would like to be able to detect consciousness from the third person perspective, even though we're very well aware that consciousness is first person and it is private. But a scientific theory hopefully could bridge this gap. So this is only one question, is why the substrate of consciousness is what it is and how do we find it? The second question is explaining the content of experience. Of course, consciousness is not just levels, it's not just on and off, but it is very different. We can experience, for instance, very different scenes. We have sensory modalities. So a theory should also tell us something about the fact that different mechanisms in the brain contribute to experience different contents. So for instance, we would like to know why visual space feels extended. Somatosensory space also feels extended. So the feeling of the extendedness of our body or on the surface of our skin. Whereas, like, for instance, other modalities such as olfaction are not the same way. They don't feel extended in the same way. We would also like to know why it feels like time flows most of the time. We would like to explain why some mechanisms in the brain are not only allowing us contributing to experience some, let's say, low-level features such as colors and edges and shades, but also we see objects. We see a lot of spots or blots on a painting. In a painting, for instance, we see a face there, right? That's a very interesting feature. We don't know how the brain really does that. We have some inklings on what mechanisms are responsible for that, but we don't know. And ultimately, we really don't know why sensory modalities are different, why pyramidal neurons in auditory cortex, when they fire, contribute sound to our experience, and pyramidal neurons in visual cortex contribute color or some other visual properties. So a theory in principle should address all these questions. So IIT is such a theory that tries at least to address these questions head on. As I mentioned, IIT is at its 4th iteration, and we published October 17, 2023 on PLOS Computational Biology, the 4.0 version of IIT. I invite everybody to read this paper and also use this paper even throughout my presentation. Actually, I think virtually every single reference I have is contained in this paper. So if you go back to this paper, you can find all the secondary literature and all the other papers that have been published by the IIT lab to support various claims. So this is a little bit like the main resource that I recommend you to consult. Okay, so we clarified the explanandum. We said, roughly speaking, what the goal is. And now I would like to spend a little bit of time commenting on the methodology of IIT. And I want to do this because the methodology of IIT is notably very different from some standard approaches in consciousness science and also science in general, because consciousness is such a special, topic and a special phenomenon that it requires a different approach. And this has been said many, many times by many people. So the first important step in the methodology of IIT is to start from phenomenology. IIT is a theory that, like Johannes pointed out, starts from a description of a phenomenal structure, what it feels like to be you right now. You could use some methods such as microphenomenology. You can just introspect, sit down like Descartes in your cabin with the wood stove and your chair, and think, what am I experiencing right now? I'm seeing likely a screen. I'm looking at some colors. I'm hearing sounds. I feel I have a body. All these things are what we mean by experience. This is one experience. It's one snapshot of consciousness. And we would like to characterize it in as much detail as possible. We would like to have a description of what it is like to be you right now as a structure of what we call phenomenal distinctions and their relations. The idea is that once we have characterized one experience, we would like to translate some of its properties into properties of the substrate, that in this case, our guess is it's going to be a neural substrate. It's going to be a portion of the physical world that is a part of the brain. And the idea here is that we can do different things. We can start by translating only the properties that seem to be true for every conceivable experience. So what we call the essential properties of consciousness that are always there whenever there is an experience. And we can try to use these properties translated into some form of observable, measurable, objective property to now study consciousness from the third-person perspective after we've gone through the introspective first-person perspective step. The idea is that we can translate these properties in physical terms broadly understood. That's what we mean by cause-effect power. We really don't commit to the existence of, charge and mass, and we don't think you have to use electromagnetic fields necessarily. We just want to describe physical properties in the most general way we can, so that then this explanation is likely to be true even when we fill the gaps. So the idea of IIT is that in physical terms, to capture really what exists physically out there, it's not enough to just look through a microscope or do some recordings. We really have to understand what's out there in terms of its cause-effect power, what we can do with this object, which is the neural substrate of consciousness, and how it interacts with itself. So for IIT, unfolding the full cause-effect power of a system really means to characterize it in physical terms completely. So for instance, we will see in a minute that it really matters in what state a system is and what are the counterfactual state that this system could enter into. And it is that these are all important properties that we can search for in physical terms because we are trying to address, we're trying to account for one essential property of consciousness that we have introspected and that we have found through introspection. So after this translation, the method of IIT is now to ask, well, is there an identity between the properties of experience, at least the essential ones for now, and the properties of the substrate, at least the candidate substrate of experience unfolded in its cause-effect power. The whole hypothesis of IIT is that if this is a good explanation of consciousness, then yes, there should be no property of experience that has no correspondence in terms of cause-effect power. And this is really the core of IIT, the idea that we can take the essential properties of consciousness, translate them into cause-effect power, and establish a correspondence. From here, we can do different things. We can ask the question, well, what about the accidental properties of experience? Right now, I'm seeing a lot of colors, and right now, instead, I'm just seeing black. So colors, at least, let's say red is not an essential property of my experience. I can have an experience where there is no redness going on, right? But sometimes there is red. So how do I explain the difference between experiences with some contents rather than other contents? So that's another question that we can ask following the same methodology. We introspect the specific properties of an experience that are not essential. We translate them into cause-effect power and try to see whether we can establish this correspondence. And then from here, we can go then to the empirical side and we can ask, okay, if this seems to hold, what can we now do? How can we validate this hypothesis empirically in healthy humans? And also, how can we just test our predictions? Can we falsify this theory because a result goes not the way that we envisioned? And the answer is yes, there are some tests, and I will talk about that. And then finally, after validating on our gold standard, which is adult, awake, conscious human beings, we can extrapolate beyond healthy human beings. And then now we are in the territory of inferences. This is not really how we can test the theory anymore, because ultimately we don't have independent evidence to, for instance, prove that an AI is conscious or a different system is conscious or not. Right. There are some metaphysical considerations, of course. I want to stress right now that the identity of IIT, we call it an explanatory identity. This doesn't mean that IIT proposes to reduce consciousness to some physical properties. It means that consciousness is what it is. It's your experience. It's the thing that you know very well, most intimately, and we're not going to take that away from anybody. That's really it's a brute fact. It's just a phenomenal fact. It's there, it's a given. We would like to explain it in a scientific way. And this means that we would like to find a way to establish a correspondence between some physical properties in terms of cause-effect power and the properties of experience. You can see this explanatory identity as a way to basically say consciousness is what a brain in a state feels like from within. So there are some physical properties in the universe. Extrinsically, from the outside, they look like physical properties, but intrinsically from the inside, they feel like consciousness. And that's what we are. We are brains, but we feel, we feel consciousness from within. Okay, so part one is going to be, I'm going to focus only on the first 4 steps of IIT out of 5 general steps. And this idea here is that we can find the substrate of consciousness before unfolding in full its cause-effect power using the last axiom and postulate of composition. And then we can translate this first step in empirical terms and see how it applies to detecting consciousness in human subjects. So, as I mentioned, there are some essential properties that IIT proposes are true of every conceivable experience. And these properties are intrinsicality, information, integration, exclusion, and composition. And these really characterize phenomenal existence. These are the axioms of IIT, which really just means the properties that if we introspect every possible experience we ever had, or any conceivable experience we could have, these properties should hold. And the idea of IIT is that we can take these very same properties, which are necessary and are sufficient, allegedly, to characterize a conscious experience, and translate them into physical existence. So properties of the substrate of consciousness that should be able to support the phenomenal existence that we are describing from the first person. And the properties are the same: intrinsicality, information, integration, exclusion, and composition. And I want to point out that there is different ways to describe the postulates, meaning the physical rendition of these essential properties. One is by looking basically at the physical substrate. So we can imagine the brain in this case as a system, as a neural network of nodes that have probabilistic functions, and they are connected in various ways. So there are synapses, and they can fire or not based on the state of their inputs. But we can also give actually a mathematical interpretation of everything that I just said by considering the substrate as basically just a set of transitional probabilities. So we can conceptualize a node. In this case, it could be a neuron or a mini column as a unit that has a probability to fire or not to fire. And we can describe this in mathematical terms using conditional probabilities. So let's dive right in. I am going to go through the first 4 axioms and postulates of IIT. Again, time is limited. I believe IIT is a theory that needs possibly more than one single talk to be understood. So I invite everybody to check out the literature if you want to know a little more. I'm just going to present you the gist of some of the conceptual foundations of IIT. And then hopefully this will allow you to at least understand the main concepts. So first of all, IIT starts from a very Cartesian stand. It basically acknowledges that experience exists. We don't have to prove it. It's just there. It's possibly the only indubitable and irrefutable truth, a la Descartes, a la cogito ergo sum. In this case, it's really, I experienced for something exists. There is something. And I would like to imagine you that you are that person there sitting and looking from their eyes outwards, having a first-person experience. And the fact that there is something there is also a property that we would like to translate into physical terms. And so now it's the task of somebody, perhaps behind them, like a scientist who's trying to understand where do we start from when we're trying to study consciousness and the fact that it exists, it feels something to be alive and to be you. How do we approach this problem in scientific terms? The translation of IIT of the bare minimum, which is really something exists, is that from the outside, from the extrinsic perspective of an external observer, at least we have to acknowledge that something must be out there in the world, the substrate of consciousness in this case, that we can characterize in terms of cause-effect power. And what we mean by this is really, there must be something that we can interact with. We can make a difference to it, and it can take a difference from us, and it can also make a difference to us. We need to be able to observe, the substrate of consciousness, otherwise we don't know where to start. And we can characterize this in mathematical terms as the idea that if we look into the brain, of course, we are building on standing on the shoulders of millennia of neurology and medicine, and we know that certain areas like the brain, some other organs like the lungs are more important for consciousness. So we can start characterizing the substrate of consciousness through, again, some mathematical formalism. In this case, we're using transitional probabilities, conditional probabilities. We can say there seems to be a unit here. Let's say it's a neuron or a mini column or a macro column. And all I care about is that when some of the inputs are on, it behaves differently than when some inputs are off. So we can perturb and observe, manipulate and observe, and we can figure out that every unit in our candidate system has some probability of turning on or off based on its inputs. And when we do this independently on a lot of units, and we set them in all possible states, and we observe the probability that the system as a whole will enter into some other states, then we can start having a description, a mathematical description of the physical substrate of consciousness in terms of conditional probabilities. We can build what we call a transition probability matrix, which is abbreviated TPM. Every time you see TPM, it just means this matrix of probabilities that basically says the probability of our system A, B, C, D, I, O, of going from state off, all off, which is all small cap, to state all off in the column, which is, again, all small cap, lowercase, it's 0.9. And the probability of transitioning to other states is instead very low, almost zero. So having this description of the system, we start our mathematical representation of the substrate of consciousness. This can be translated then into a substrate graph. So we can then conceptualize our units as being connected and having different weights, different synaptic weights. So we can describe mathematically the probabilities with the transition probability matrix, but we can also represent it as a graph, as a system. So this is the idea, is that if something exists intrinsically, for my experience, there must be something out there that I can observe and perturb in order to even start my explanation of consciousness. But this is, of course, only even the 0th axiom. It's not even the first. It's before everything. The first intrinsic property of experience is intrinsicality. It's the idea that not only I have an experience, but experience is intrinsic. It is for myself. It's always from my own point of view. And now, when we try to translate this in physical terms, we already reach an interesting conundrum here, because there is no privileged intrinsic perspective in physical systems. We can consider a system from the point of view of God or the universe or our microscope or whatever we want. We can focus our attention really on, there's no borders, there's no privileged perspective. The idea is that if consciousness is intrinsic, has a perspective, it means that there must be a way to characterize this perspective in physical terms. So the attempt here is to translate this as the idea that the substrate must take and make a difference within itself. So we must be able to describe, for instance, the fact that my own perspective is from this point of view. And to do so, we can set a candidate border around the substrate that we want to evaluate. And we can fix as background condition everything that is outside of this specific subset. And then we can constrain our mathematical representation of the substrate using only, let's say, the cause-effect power that the substrate has upon itself, excluding everything that is outside. So for instance, this relates to the fact that we know that the brain is able to specify, contribute, various mechanisms are able to contribute to conscious experience, even when we are disconnected from the environment. When we are dreaming, there are literally some neurochemical ways to disconnect from the environment, from afferent pathways, and yet consciousness still happens. So there must be a way in which these mechanisms here make a difference to themselves regardless of what happens outside. It's not, of course, regardless, because blood pumping, the oxygen in the room are important background conditions, but they're not directly contributing to our to our experience. So we can do this, of course, including different subsets. We can focus on one subset that is smaller or larger. This is going to have to be done for all the possible subsets if we want to have a complete representation, complete account of the substrate of experience. So we can move then to now a representation of our transition probability matrix that is only the system upon itself, instead of including other units. In this case, we have excluded I input unit and O output unit, and we have just kept A, B, C, D, which are this candidate units, let's say neurons, that are inside their candidate substrate of consciousness. So we can move then to another property of experience, which is information. And information is a very interesting property because it really captures the fact that our experience is always specific. We cannot have an experience with some just generic content that is unspecified. It is this one. I'm seeing either blue or red or green or a combination of all these colors. Or I can see a color that I can't really name. It's even better if you think about the taste. Maybe I'm feeling a taste. I don't know. It's I don't know, cardamom. But it is a taste. It's a very specific taste I have in my experience. And of course, every experience is very different from a lot of other possible experiences. This idea is captured in physical terms through the language of information. The idea is that in order to be specific, the substrate of consciousness must have the cause-effect power of the substrate of consciousness must be also specific. So the substrate of consciousness must be in a state, just like my experience has a state. And it must also select a cause-effect state, meaning this state must be specifying some information about its cause and its effect. And so to translate this in physical properties, in operational properties, first, we take our candidate system of nodes, we set them in a state, we observe, for instance, this neuron being on, and here I'm representing A in dark and capital to say this node is on and all the other nodes are off. So this is a specific state. Before I didn't talk about any specific state, and I had this big transition probability matrix going from any state to any other state. Now I'm saying, no, this experience corresponds to the brain being in this state. And what we can then do is that we can ask, okay, but what does being in this state mean? Every neuron, just by virtue of being on or off, doesn't really convey much information. What really matters for IIT is the fact that for a node, actually for the system as a whole, to be in a state means that it is specifying information about the probability of states it came from and the probability of states it will go into. So we can find all the input states that are possible. We can measure the likelihood that the system was coming from those states. And we can use like a metric, which is called intrinsic information, to see what is the state, in this case on the cause side, that the system specifies the highest information, intrinsic information about. So from the point of view of the system, being in this state, not knowing anything about what happens in the rest of the universe, the system is specifying maximum information about a past state that in this case is beyond A, C, D, off. And we can, of course, do the same on the effect side. We can take our current state and ask what is the state that the system has the highest intrinsic information about that is instead on the effect side, meaning on the output side, or a future state. So the mathematics of this course is very complicated, and I invite you to consult the papers, but this is just to give you a gist of the idea that there is a measure, intrinsic information, that in IIT plays the role of selecting a specific cause-effect state from the point of view of the system, which is intrinsic because it has a specific border, in this case, the candidate system. And the idea is that in every possible state we observe the system, the information that is specified is going to be, it's likely going to be different. So in this specific state, as I said, the cause state of the system is going to be B on, everybody off. So when A is on in the current state, the highest information from the intrinsic perspective of the system is specified about the past state, with B being on, and on the effect side, C being on, which means, if you want to simplify, the system has to make its best bet from its intrinsic perspective about what happened just before, what caused its current state, and where the system itself will go, what's the next state. And this is the cause-effect state that the system in this current state is specifying. And of course, systems in different states, the very same system, if every node was off, would be specifying a different cause-effect state. And this in IIT corresponds to the idea that every experience, by virtue of being what it is, having the content it has, is different from other experiences. If an experience was different, there would be different counterfactuals and different contents. Okay, so we can move to the third axiom and postulate, which is that really it's not enough to have an intrinsic and also a specific cause-effect power in order to match all the essential properties of consciousness. Notably, consciousness is integrated. Experience is unitary, it is a whole, it is irreducible to separate experiences. It's inconceivable to have an experience that is not one. We could have separate contents of experience, but they are always co-experienced by one subject. Otherwise, there would be two subjects of experience. Again, how do we, from the point of view of a scientist with a physical system in front of us and our mathematical representation, how do we check that this substrate, alleged substrate of experience, is a unitary whole? The idea of IIT is that we can measure this by asking whether the substrate specifies this cause-effect power as a whole set of units that is irreducible to subsets. And to check whether this is true, we can partition the system and see whether partitioning the system makes a difference. So the whole idea is that if I have two systems that are not interacting with each other, cutting between these two systems shouldn't make a difference to how they behave. If two parts of a system are instead interconnected, any minimal cut I make to any of their interconnections is going to result in a loss of information, is some sort of effect. And in that case, I can know that the system is integrated and I can quantify how much. So in mathematical terms, now we can use phi, which is a measure now of integrated information. This is small phi, system phi. And we can do exactly like we did before. We actually cut the connections between different nodes, or noise them really. And then we can measure how much the intrinsic information that we computed before changes if now it is compared to a partition version of the system. And then we can do this on the cause side and on the effect side. And to do so, it means that we may end up with two different values, like in this case. Of course, one system has to be one, and it can only exist as much as its weakest link, so to speak. So the idea is that between these two values, we have to pick the minimum. If a system makes no difference to itself on the cause side, but it makes a difference to itself on the effect side, we would say that the system is not integrated. It doesn't exist as one. Okay. So lastly, our fourth postulate is exclusion, and this in phenomenal terms is the idea that experience is definite. It is a whole. It has a specific border. It includes what it includes. For instance, in my experience right now, there is certain visual field, there is sound, there is my bodily sensations, but there is no such thing as an experience of my blood pressure or my level of blood sugar, even though that sometimes might peek through some other, of course, experiences. So the general idea is that we should be able to explain also why the substrate of consciousness is this definite set of units. It is not larger and it is not smaller. So we could, in principle, find mechanisms in the brain, as I said, like some neurons are probably monitoring my blood pressure right now, but why don't they contribute to experience while some other mechanisms do? The idea of IIT is that different candidate systems can specify information, in particular integrated information, but the one that corresponds to my experience is the one with the maximal integrated information. So here, the idea is that what exists is what exists the most. And we can do this by, instead of conditioning and using in our intrinsicality step only 4 nodes of, in this case, our simplified 6-node network, we can compute integrated information, system phi, let's say for a subset of it, let's say only 3 nodes, A, B, C, or we can compute it for the whole network. And the conjecture, right, is that maximality will really tell us what the objective border is. This also applies to the grain. I mentioned that we don't really know whether neurons or mini columns or molecules are really the units that allow us to account for conscious experience. Exclusion should also tell us at what grain system phi is maximal. If we did the same analysis, and instead of considering B1 unit, let's say 1 millicolumn, we were to go inside and we were to perturb and observe all the neurons that make up this mini column, now we would have a much bigger system with bigger number of units. And if system phi were actually higher, then in IIT would predict that that should be the scale at which consciousness happens. That's the real grain of the substrate of consciousness. And similarly, we can do the same by macroing units. Instead of taking neurons, we could take mini columns, and phi should be high wherever there is a unit that is really relevant for conscious experience. Okay, so as I said, this is a very short presentation of the axioms of IIT and postulates. Whatever you got from that, I would like now to invite you to see where this can lead. And the idea is that we can go back to our first question and ask how these first postulates up to exclusion allow us to make some predictions about substrate of consciousness, and in particular, to detect consciousness in human subjects. So many of you are probably familiar with the fact that in the past 20 years, the science of coma and disorders of consciousness have developed some amazing tools to detect consciousness in unresponsive patients. For the ones who are not familiar with what I'm talking about, imagine you're a neurologist, you have a patient who maybe went through a stroke or an accident, and they have some vital signs that are okay. There is brain activity, but they are not responsive. Maybe their eyes are open, they have some autonomic functions, they even breathe, but they're not responsive. So how do we know whether they're conscious or not, whether they are actually hearing what's happening in the room around them, whether they are feeling pain or pleasure, or they have the capacity to feel pain and pleasure? So usually in neurology, one of the main tools is, for instance, the Glasgow Coma Scale, which is a behavioral tool. We, for instance, ask the patient to follow our finger and see whether they do it. We touch their extremities and see if they move, all these kind of things. But this sometimes, of course, doesn't really work. You can imagine a person who is tetraplegic, completely paralyzed. They cannot move any muscle, not even their eyes. And so it would be very hard to get any sort of behavioral response, bodily observable response. So in 2006, an amazing paper came out which showed that actually by having patients in an fMRI machine and asking them to perform some imagery tasks, it could be possible to check whether a patient can respond to our answers. And this was a brilliant idea. In this study, Owen and colleagues studied a patient who had extensive lesions in the frontal cortex. And so on control studies who are healthy patients, healthy subjects, they were able to ask them to imagine playing tennis compared to instead imagining to navigate their home, going from one room to the other. And these two imagery tasks light up very different regions in the brain. There is a bold signal with fMRI that shows activity in different regions. So they, as a first step, asked this patient who was non-communicative to do the same task. They asked them, if you hear us, please imagine playing tennis for 30 seconds. And then now imagine to walk in your apartment for 30 seconds. And they noticed that there was a very similar activation. This patient was non-communicative. It seemed like they couldn't follow any request of a task, but they were able to imagine things as much and as well as healthy subjects. So in a subsequent study from 2010 and the lab of Martin Monti, they actually use this methodology to communicate with patients who are who've been diagnosed as vegetative state or minimally conscious state. So patients who would not reply to any cue, and they would not be able to follow any command and show behavioral response. They actually this time told them, we're going to ask you some questions. If you want to answer yes, imagine playing tennis. If you would like to answer no, then imagine do this spatial navigation in your house. And what they found out is that some patients who were diagnosed as vegetative state based on observable behavior were actually able to answer these questions about their personal life with 100% accuracy, just like healthy subjects. And they were also able to say yes and no to questions such as, are you in pain? Are you hungry? Is there something that you would like us to do? So this was an amazing way to go beyond observable behavior, such as bodily movements, and detect consciousness, because really, when we can communicate with somebody, that's one of the main cues we have, again, from the external point of view, that they are conscious, that someone is in there. There is something it is like to be them. Although, I just want to add that if you're interested, there was actually a patient who was a locked-in syndrome patient. So they were completely conscious, but mostly paralyzed. They could just blink with one eye. And it took a long time before the nurses and the neurologists realized that they were perfectly conscious. This patient started communicating with a nurse by blinking while the nurse was reading the letters of the alphabet one at a time, and ended up throughout the span of 5 years writing a book that is about his experience. And there is an amazing book called Le Scaphandre et le Papillon, also a movie called The Diving Bell and the Butterfly, if you're interested in this story. This is all great. So we could detect basically covered locked-in syndrome patients who are conscious but cannot move any muscle through mental imagery. The problem is that what happens if somebody does not reply to our answer? If we ask them to imagine to play tennis and we don't see anything on the screen. Well, there is a problem here, right? Because even though we're using mind reading or we're using neuroimaging, we're still asking a question and expecting an answer. And this is a form of behavior. It's just one step, removed from bodily behavior, but we're observing an answer, a reply that requires volition, that requires the intention to do something and the capacity to do something. So we might have patients who are maybe not hearing our commands and they are perfectly conscious, but we will never know. So according to IIT, there should be a way to look at the substrate of experience and check whether the essential properties that I just mentioned are satisfied by the substrate of experience, regardless of our ability to ask for a question and observe an answer in terms of bodily behavior or even mental imagery. So the idea of IIT is that really we can boil down, condense the 4 postulates that I presented into, let's say, only 2: integration and differentiation or information, and check whether at least these 2 properties are present so that we can get a rough estimate of integrated information in a real brain. So the idea here, if you see my mouse, is that when we have a complex network with both integration and information, stimulating part of the network will spread a sort of cascade of activation in an informative way that is differentiated. So every stimulation will cause a different pattern of activation, but it will also be integrated in the sense that this stimulation will not stay local. It will travel throughout the system. Loss of integration means the stimulation will stay local. Loss of information means that wherever we stimulate, whenever we stimulate, the whole system replies in the same way, reacts in the same way. It's as if I was showing you a picture of mountains and you would just see darkness. I was showing you a picture of a seaside and you would just see darkness. That's a loss of information, so to speak. So there is a way to, instead of asking a question verbally, to actually trigger an activation, a little bit like we were doing in the existence step. We can perturb directly the system, setting some nodes in an on state, so changing the node of the system, and see where the TPM basically goes, and observe whether there is integrated information in the system using perturbation and observing with an electroencephalogram the response of the brain. So the transcranial magnetic stimulation does the stimulation, the EEG records the effect on the brain, and then we can take the response in different states of consciousness, paradigmatically our gold standard, healthy subjects during wakefulness, and maybe non-REM deep sleep or anesthesia. And then we can use algorithms such as the perturbational complexity index to take the data about the response, compress them a little bit like you do with WinZip, or when you're trying to compress a lot of files that are very big on your computer, you can exploit redundancies and basically compress whenever there is not a lot of information and see whether this signal has a lot of complexity or low complexity. And this is what gives us an index called PCI, Perturbational Complexity Index, which is related to integrated information. It can be seen as an approximation. We can talk about the links between the 2, but that's the general idea. So everything I said about stimulation is going to be much clearer in this video that was from the 2013 paper by Casali and colleagues. And this is the paper from and the video is in the supplementary material of this paper, and I will have to narrate it because there is no sound. So here you see the PCI machine, the TMS machine with EEG, and a subject that in this case is getting stimulated. The idea is that transcranial magnetic stimulation triggers activations in one region of the brain. The EEG records how far and how complex the activation spreads within the cortex. When there is consciousness, there is both integration and information differentiation. The stimulation travels through time for at least, let's say, 300 milliseconds. It's very complex. Brain areas light up in different ways with a complex pattern, and the stimulation triggers some global activation. So it spreads, it doesn't stay local. We can then compress, binarize, normalize this data, and we can find one value, which in this case is the value of perturbational complexity index for consciousness. Then we can repeat the same experiment when there is unconsciousness, a loss of integration, for instance, during deep sleep. And what you notice that this is real brain data, the activation stays very local. So there is a lot of integration, right? And it's also much shorter in time. So if we binarize and we compress this response, we find a much, much lower value of PCI. So an approximation of a loss of integration. We can also have unconsciousness with a loss of differentiation or information. And this happens when we stimulate one area of the brain and the whole brain lights up. It's very integrated, but it activates in a very stereotypical way. It just does the same thing, which is, again, very compressible. I can tell you letter A 100 times, and this is a very compressible message. And this is, for instance, what happens in epileptic seizures. So in the studies, they repeated this measure of PCI on a lot of conscious conditions, such as wakefulness, and then unconscious conditions among, for instance, deep sleep, but also a lot of different anesthetics in a supra-anesthetic dosage. And then finally, they repeated this experiment on patients who were diagnosed with either vegetative state, minimally conscious state, or locked-in syndrome diagnosis. And the results I'm going to show you in a better picture showed that there is one cutoff of PCI, which is 0.43 something. And all the wakeful patients had a PCI that was above this value. All the patients in the control group that were either in deep sleep or under anesthesia were below the 0.3 mark. And then all these patients that were either diagnosed with some disorder of consciousness were placed throughout the entire spectrum. And it actually correlated really nicely, because the patients with a diagnosis of vegetative state and a Glasgow Coma scale, so behavioral scale value very low, like below 5, all had PCI below 0.3. And patients who were locked in, meaning they were perfectly conscious and diagnosed as locked in, perfectly conscious but behaviorally unresponsive, they were all above, like basically indistinguishable from wakeful patients. And then patients with minimally conscious state or who emerged from a coma and had higher values of basically behavioral performance, they were all in the spectrum closer or further away from the PCI of the wakeful control group. So this study was in 2013. In 2016, there was another study, which is another one of my favorites, which repeated the experiment with PCI on a much larger scale. In this case, we have more than 150 patients. And this is a study by Casarotto and the lab of Marcello Massimini in Milan. So in this graph, you can see that the PCI was applied on subjects who were awake, and they reported immediately whether they were conscious or not, and on healthy subjects still, who instead did not report at all whether they were conscious or not, even when asked after some time. And then some subjects who reported that they were conscious at the moment of the stimulation, but only afterwards. And PCI correlated very nicely, showing that all the subjects that were awake and healthy and reported that they were conscious had a PCI above, in this case, 0.31, which is PCI star, the dashed line. Also subjects which reported that they were conscious but were locked in syndrome patients, or who underwent a subcortical stroke or cortical stroke. So all the subjects who reported that they were conscious, PCI said yes, the value was above 0.31. There was no subject with a PCI lower than 0.31 that reported they were conscious. Conversely, every subject that had a PCI lower than 0.31 reported that they were not conscious even afterwards. And these were subjects who were in deep sleep or under anesthesia. Some subjects had a PCI above this threshold and reported that they were conscious after a little time when asked, were you conscious 10 minutes ago? And it was either because they were in REM sleep, they were dreaming, or because they were disconnected from the environment because they were under ketamine, but they were still conscious and experiencing a lot actually, but couldn't report there and then. Again, I want to highlight that there was no case of an immediate report of somebody being conscious with a PCI that was lower than 0.31. And there was no case of subject who didn't report that they were conscious there and then with a PCI that was higher than 0.31. The delayed report is a separate value. The same study applied the same criterion on instead patients with disorders of consciousness. And what you can see here is that, again, our PCI star of 0.31, we have some patients that were diagnosed as, let's start from the minimally conscious state, which is there is behavioral responsiveness, even use of minimal language. And all these patients had PCI that was higher than 0.31. Whenever patients were diagnosed as vegetative state, because the behavioral responses were below a certain threshold of the Glasgow Coma Scale, now the PCI values sometimes gave basically a zero value, meaning that there was absolutely no integrated information. Even in patients who had a relatively high behavioral score, like let's say around 6, there were some patients who had a PCI that was lower than 0.31, and again, across behavioral evaluation scores. And then interestingly, there were some patients who had PCI values that were comparable to wakeful healthy patients, but had a very low behavioral responsiveness score out of the Glasgow Coma Scale. So arguably, these patients could be patients who are covertly conscious. They are conscious, but they cannot behave in such a way that we can detect consciousness. And this goes together with the evidence that actually there's a wide literature that shows that almost 40% of diagnoses of vegetative state might actually be misdiagnosis. People might be perfectly conscious but unable to communicate. So PCI is an interesting tool that approximates some of the mathematical formalism of IIT and makes it applicable to real brain case scenarios. And it might have direct implications on not only the diagnostics of disorders of conscious, but also the prognostic. There are studies that show that a high value of PCI in a patient who does not show behavioral complex responses is a good prognostic factor, meaning that that patient is more likely to emerge from the coma. There's a literature that you can find quoted, for instance, in this Casarotto paper. Okay, I'm going to skip this slide. So I showed you how the first 4 postulates of IIT allow us to at least tackle the question that I think most theory of consciousness are trying to address, which is, what is the substrate of experience? Why do some regions of the brain, some patterns of activity matter for consciousness? And how do we detect whether subjects are conscious or not by applying quantitative measures? The idea of IIT is that PCI is an approximation of integrated information and can allow us to do so in a non-behavioral way. So before I go to part 2, which is about the content of experience, maybe we can have a little break and I can ask if people have any questions.
Sure. I see one hand raised already. Beljan.
Thank you. I just wondered, by the way, this has been very fascinating and it's so clear and wonderfully illustrated. Thank you. I just wondered if you would comment, and I'll just describe it quickly, an experiment that goes back to the 60s at St. Anne's Psychiatric Hospital, where I was the control. My husband was they wanted to study the brain of an artist, and I was the control. I believe they gave me a shot of psilocybin. I was hooked up to the EEG, and I heard the 2 neurologists across the room suddenly say, "Elle dort profondément." She is deeply asleep. She is unconscious. And I said, "I am not asleep. Please stop the experiment." I was worried if my brain said I was asleep and I was perfectly conscious, what was happening.
Thank you. Thank you for the question. This is absolutely very interesting additional evidence that unfortunately, like back in the 60s, right now, we are still in the dark about measuring consciousness and detecting consciousness. I mentioned the study on ketamine, and psilocybin is absolutely a very fascinating alternative case where people can be having very vivid experiences, but completely unreactive. And we have of course, other drugs and other psychedelics. So there are studies that apply PCI with psychedelics, and this has happened in animal models, non-human animal models, and human models. And the idea is that, well, this is a great opportunity to falsify IIT. If PCI applied to a person who's having a very vivid experience turn out to be very low, then IIT would be wrong. Like, this would just be a really deep, a really deep hit to the foundation of the theory. But the converse is also true, that if instead we show that there is not only disorders of consciousness where people can be conscious but unresponsive, but there's all sorts of other states. It can even be a very deep state of meditation besides psychedelics. Then IIT can actually provide some of the tools to approach these states, and also, of course, have inform medical practices. Like in this case, they should have known that you were conscious if you were monitored for let's say PCI. So thank you for the question, and yes, that's very relevant.
Thank you very much.
Matteo, maybe can you stop sharing the screen so we can
Yes.
put people in the spotlight for questions?
Okay.
And we will start from Paul.
All right. Yep. Yeah, okay, go ahead.
Yeah.
Well, thank you so much for such a clear and comprehensive review of the integrated information theory. And, it's wonderful to see how the theory and the experimental data behind that have advanced our understanding of cognitive processes. I'm just wondering, how would the integrated information theory explain experimental data from some other areas about consciousness and about experience in particular? For example, well, let me give us 3 quick examples. One would be the cardiological data, for example, from von Pimmel and others, showing that there is some experience continuing even when brain is not functioning anymore. It's completely out of processing during the near-death experiences. Number 2, the data, experimental data by Russell Targ, for example, remote viewing, where obviously there is experiences without sensory input and verified. And of course, and also data from, let's say, neurosciences, showing that you can have very different quality of emotional experience, and yet you have essentially the same neurobiological data in the brain.
Thanks. That's a very interesting question. So, so if there was evidence that there is minimal brain activity and a vivid experience, again, actually IIT would be a theory that would be suited to answer the question possibly in the positive by showing that minimal brain activity doesn't mean low integrated information. We could, in principle, like in states of deep meditation, a lot of areas of the brain, especially the cortex, can be very silent, but people report having a vivid experience, actually feeling even more present than usual. So IIT doesn't really necessarily say that low activity means no information. It matters the amount of integrated information. So it could, in principle, support this evidence. It could also, although, be falsified by this evidence, because if you could show that there is minimal activity or zero brain activity, and yet there is an experience, people report having an experience, well, IIT would be falsified, because for IIT, some activity, or at least the capacity of neurons to fire if stimulated, that they don't have to fire right now. They need to have cause-effect power. If that is not present, integrated information is not present, and consciousness is present, then IIT would be falsified. So I could see it go either way. But thanks for the question. This is the type of evidence that should be reviewed and should really be brought in contact with the other research. If that's okay, I would go to the second part and maybe gather more questions at the end.
Right.
Thank you.
Yeah, because I see we are short on time, or not short, but you have the second half of the
Yeah, I have a lot of slides, but it's modular. I can skip some parts.
Okay.
I put together a lot of stuff here. Okay.
Please
so,
keep the questions for later.
Sure, thank you. So I'm going to share the screen again. Yeah, 1 second. Sorry.
Perfect.
Sorry, I have to just give me 1 second. I have the presenter's view that is.
Sure. While Matteo fix this technical inconvenience, I will. We have a great announcement to make. Alex asked me to remind everyone that we have the Paris Center as an upcoming event, which is next Wednesday. We will have the pleasure to have a conversation between Alex Gomez-Marin, who is the director of the Paris Center, and Christoph Koch, which is a very famous neuroscientist that already came up a few times during this series. And I should remind you that this event will start at 7 p.m. rather than 6 p.m. So 1 hour later than usual for this kind of event. And so please, Matteo, go on.
Thank you. Thanks, Francesco. That sounds super exciting. Thank you. Okay, so the second question that I wanted to address, which is mentioned also in the fallacy of misplaced objectivity paper, authored with Francesco, is really, we would like, with a theory of consciousness, to explain not only when consciousness is present or absent, high or low, if you think there's levels of consciousness, but we also, and maybe even personally, I think more importantly, we would like to have a way to explain and to understand the content of experience, again, from an objective outside viewer's perspective. And this means explaining why modalities feel the way they do, and whether somebody is experiencing something like pleasure or pain or some sort of emotion. And this becomes, of course, again, very important for non-communicative patients, but this can extend to pretty much anything, really. And as a philosopher or somebody with a background in philosophy, of course, this is an attempt to explain qualia scientifically, to at least say something about qualia from a quantitative perspective, which puts IIT, I think, at the center of the stage for ambition, and also it makes it a very interesting theory that really tries to go in a direction that very, very few theories dared exploring. So what I'm going to present now is an attempt to apply now the last postulate, which is the postulate of composition, that tells us once we have identified the substrate of consciousness, we really want to unfold the cause-effect power in full, and there should be a correspondence between the properties of a cause-effect structure, which is this mathematical object that is supposed to represent really all the cause-effect power of the mechanisms inside the substrate of consciousness. And the idea is that there should be a correspondence between properties of my experience, essential and accidental, and then properties of the cause-effect power of the substrate of consciousness. And the agenda of IIT is to start modest and approach the content of experience starting from the fact that most conscious experiences are characterized by a feeling of extendedness of the visual space, and then a flow of time, and then the fact that we can recognize objects. And then there are local qualities such as color and pain. So in the second part, I am going to introduce composition rather briefly, and then go to at least space and maybe time, we'll see. So composition is the last axiom and really captures the idea that our experience is not just monolithic, it is structured. There's a lot of content. It is composed of a lot of distinctions, so I can distinguish, for instance, the sounds that I hear from the colors, from the fact that I'm seeing a face on the screen. And there are a lot of relations between these contents of experience. So I can highlight, for instance, a square that I see on the screen, and the fact that there is some blue in my experience, but also the square is blue. So there are relations between all these components of experience. And the idea is that I can describe a single snapshot of experience, my experience, as being a structure with all these components. In IIT, this is translated into the idea that the substrate of consciousness is not just this system that specifies information about a cause and an effect state as a whole, and it is irreducible as a whole, but the system is actually constituted of a lot of different mechanisms. And each of these mechanisms is actually contributing some information, some cause and effect power about other mechanisms within the system. So neurons in my visual cortex are specifying information about other neurons in visual cortex. And likewise, neurons in visual cortex with neurons in associative cortices together are specifying information about, for instance, multimodal experiences and contents of experience. So this is what yields what we call really the cause-effect structure. So now I am going to go very rapidly through these slides. So this is just to give you again the gist of what composition is and how we end up with this cause-effect structure, but you can look up the papers for a complete description. So first of all, IIT recognizes that mechanisms don't have to be first-order mechanisms. There is emergent properties of assemblies of units, higher-order mechanisms constituted by more than one unit. So, for instance, a mechanism that is constituted of unit A and B together might specify some information that is irreducible to the information that is specified by A and by B separately. So composition is a step where we can apply again all the postulates safe for composition at the level of a single node of the system. Now we are not talking about the system as a whole, we're talking about one node or a subset of nodes in the system. And you can check out this paper called Causal Reductions and Causal Structures that I co-authored with other people here in the lab that makes a simpler point about the fact that even without going to consciousness, causal reductionism, so the idea that individual neurons, the state of each individual neuron is all we need to know to explain, to have a full causal account of a system is highly problematic. So we can have cases in which a mechanism, for instance, CD in this picture on the bottom right, CD together specifies some information about input A and B that neither C nor D specify individually. So there is more information in a mechanism, higher order mechanism, irreducible to the first order mechanisms. And you can notice that integration is applied, information is applied in a similar way. So a cause-effect structure is basically composed of distinctions which are take these mechanisms, all the orders of mechanisms, so not only A, B, C, D individually, but A, B, A, C, A, B, C, A, B, C, D together. And we can ask whether they specify cause or effect information about any other subset of units in the system. So for instance, we can discover by taking the TPM that you see in blue on the right here and doing some mathematical operations, we can discover that unit C is specifying some information about A as its cause, being in state off, and unit D as being its effect in state off again. And we can repeat this check for irreducibility, asking whether a mechanism contributes intrinsic and integrated information to the structure of the system for every subset of the system. So we can find out that CD together, they also specify information that is irreducible, and other mechanisms do so too. I'm going to skip a couple of steps here to show you that, for instance, in this system of 4 units, we actually have 7 mechanisms that are specifying different amounts and qualitatively different integrated information about other nodes within the system. So we can take this all together and put it into our representation of the cause effect structure on the left, and then we can also translate the idea that contents of experience are also related with each other by asking whether these mechanisms in the cause effect structure overlap with their causes and effects. So they are related in the information they specify about other mechanisms, other nodes in the system. So we end up with a structure that is made of distinctions that specify causes and effects, and they relate by overlapping on their the information they specify on other subsets of the system. So the step of composition allows us to unfold the cause effect structure based on a substrate. And now the attempt of IIT is then to show that we can address more questions about the content of experience if we unfold some substrates. And I'm going to start by talking about the experience of the extendedness of space. So I would like you to now consider your experience when you're looking at a dark sky, in this case, a beautiful depiction of the Magellanic Cloud, or a portion of it, and the fact that you see a lot of little specks of light, and your experience is very rich. It is very rich not only because there are all these specks of light, but really because what you are seeing is all these little regions of space that I'm now highlighting in yellow. Like all these little regions of space are all there all the time in your visual field, right? And even when you just see dark, it still feels extended. There's a lot going on there. It is this canvas in front of your eyes. It doesn't disappear, right? So much that if I just shine again all those little contours, well, they are still there. And now if I make them disappear again and you fixate in the center of the visual field, well, now there's just blackness, but all those spots that I highlighted, they are still there, right? So the visual field is this very complex thing that even when there are no discontinuities or no contents within it, it feels extended. It's a very stable, solid piece of our visual experience. So the intuition of IIT is that this should be accountable in terms of cause effect power. Just one disclaimer, what space are we talking about here? I'm not talking about the external space, for instance, the space that physicists talk about. We're not trying to explain space-time in terms of, the space in which physical objects interact. We're trying to explain the visual, in this case, the space that we experience in our vision as visual space. We could also be talking about somatosensory space, so the experience that our body is extended. And why is it interesting to talk about space as a content, as a qualitative content of experience? Well, because it is, first of all, as qualitative as paradigmatic cases of qualia, such as color and pain. It is there in our experience. It characterizes some sensory modalities and not others. So, for instance, it doesn't make much sense to ask whether a smell is to the left or to the right of another smell. Maybe for a dog it does, but in this case, space is very different from smell or maybe taste. We can have, of course, other types of space. We can describe the color space, but that's a different acceptation of the one I'm using here. But then second, it's also interesting because there are functions that come with the ability to detect space. So for instance, we know that in the brain there are cortical and subcortical pathways that are able to basically mediate functions such as eye fixation. So in this little picture here, you can see in blue, there are some cortical pathways that go from the retina to LGN, and then they project to some grid-like areas of the brain, which are occipital visual cortex, parietal cortex, where there's a lot of lateral connections, and everything that is activation to these areas of the brain are connected to an experience of visual space, such as a dot moving in space. But there are other pathways. So, and ultimately, when we see a dot moving in space, and this correlates with activation in our visual cortices, this leads to then activation of some cranial nerves that direct the eyes. So there is a cortical pathway to perform a function such as fixation, but there are also subcortical pathways. And for instance, in gray, you can see the ones that go from the retina to the protectal nuclei, and these are all areas that instead do not have the grid-like architecture that we find in visual cortex specifically. But these systems that are also, by the way, faster in allowing us to perform quick fixation are engaged in a subconscious level. So we can move our eyes with saccadic movements, or when we are performing some attention task, much, much faster. It's almost as if it was like a reflex. So you know the difference between a reflex behavior and a mediated volitional behavior. So why? The substrate of eye movement and visual fixation that is in the brain and involves the cortex gives rise to an experience of spatial extendedness, and the one instead that is subcortical and does not have lateral connections does not contribute to experience. There must be something about experiencing spatial extendedness that is connected to the difference in these substrates. So, fantastic paper that came out in 2019, authored by my colleague and friend Andrew Hone and Giulio Tononi from the lab, addressed exactly this point. Why does space feel the way it does, and how do we explain spatial experience by applying the tools of IIT? I agree with Johannes. He mentioned yesterday that this is probably one of the first papers in maybe in hundreds of years where people really try to describe one content of experience, in this case, the extendedness of space, and tried to provide an explanation in structural terms. So now the question is not anymore, what is the substrate that is the substrate of consciousness as a whole, but it is what is the substrate of some content of experience. In this case, a subset of the cause-effect structure is going to contribute the experience of space. And in this paper, inspired by the evidence that the areas of the brain that seem to contribute to our experience of the extendedness of the visual space are grid-like and have lateral connections. Like here I have a depiction of lateral connections in visual cortex, and you can see mini column being laterally connected, and some evidence that the connections are actually hex grids. This sort of evidence, we know visual cortex relatively well, right? It's one of the parts of the brain we know the best. So in this paper, Andrew and Giulio created a simplified version of a grid. In this case, it was a 1D grid instead of a 2D grid, but it can be expanded. Of course, you can demonstrate that whatever. You can define a space in 1D and extend it to 2D. And they unfolded the cause-effect structure and showed that some of the key properties that make space can be found in the cause-effect structure. So this is a very long story. So again, I invite you to consult the paper. I'm just going to show you quickly, just again, to give you a sense, mostly visual, of what this looks like. So in the paper, they claim that a space, first of all, what does it mean that visual experience feels extended, that there is an extended feeling of space. Space is extended. Well, there are some essential properties that you can use to argue that whenever these properties are satisfied, then something feels extended, is a space, basically. And these properties turn out to be reflexivity, inclusion, connection, and fusion. The gist is that by taking the essential properties of an accidental property of experience, space, and translating them into properties of distinctions and the way they are related of a cause-effect structure that is unfolded by a substrate that we know is very similar to what in our brain contributes this content of experience, we should be able to establish a correspondence. So we should be able to find resemblance between the properties of phenomenology and the properties of this cause-effect structure. And the idea here is that what you see in the middle is a sort of abstract representation of these properties that apply both to phenomenology and to cause-effect power. So let's start one by one. Our first property is that in space, we have reflexive distinctions. We can define a space as, first of all, something that is made of spots. If we can't zoom in and zoom out and there's no different spots that we can highlight in a space, then that's not a space. It's just one thing, right? It's either a point or it can't even be really a space because a space needs to have components. This is translated by unfolding the cause-effect structure of a 1D grid, a 1D grid, by showing that all the distinctions in a 1D grid that has lateral connection, all the distinctions specify causes and effects that are related to themselves. So you have larger distinctions. So for instance, mechanism BCDEF here specifies a cause over CDE and an effect over CDE. And then mechanism CDE instead specifies a cause over D and an effect over D, but they are related. Their cause and effect are related. And you have all these mechanisms from this 1D grid that specify all these distinctions that relate in this way. And you can show that all the distinctions here, I'm just showing the label of the distinction, I'm not showing the causes and effects. All of these distinctions satisfy reflexivity. So this is the first property that is relevant for space. The second property is that something is a space if the spots include each other, meaning they are included by other spots and they themselves include spots. If we don't have this inclusion ordering, then there is really no location within a space. There is no nesting, so to speak, of spots. And this, of course, has a translation in topology and mirror topology. And I invite you to consult the paper for these details. So inclusion is also satisfied by the distinctions unfolded from a 1D grid with bidirectional connections. And this is visible because if we take a larger distinction such as BCDEF, then you have relations that I'm depicting as these yellow edges between the causes and effects of a larger distinction and the causes and effects of a smaller distinction. And interestingly, everything is very symmetric. The way in which BCDEF includes BCDE and CDEF is the same. It's just a relation of inclusion, even though they are slightly offset, the two smaller distinctions. And again, in a cause-effect structure of unfolded from a space grid, from a 1D grid, a lot of distinctions satisfy inclusion. Distinctions also fuse, meaning that if we look at the patterns of causes and effects, we can always find that when two distinctions are included by a distinction, they also, their union is identical, is equivalent to the distinctions that include them. And this is an important spatial property because it really means that space has no holes. In our experience, two spots, when they are neighboring spots, there is always a spot that includes exactly those two. If this wasn't the case, there would be holes. That wouldn't be the space that we experience in our visual experience. And again, most distinctions satisfy fusion. And then finally, distinctions also connect, meaning they partially overlap, and their overlap is another distinction. And this is another very important property, because if we just had spots that included each other, but they weren't partially overlapping, then there would really be no intrinsic ordering, right? Spots wouldn't be neighbors to each other. They couldn't connect in such a way that we can tell which one is ordered in this horizontal dimension with respect to the others. So the idea of IIT is that we can take the extendedness of space, characterize it, and explain its essential properties, which are the ones that I mentioned. And we can also then explain some secondary properties that are derived. And here, I'm going to skip on this, but for instance, the location of a spot is really where it is placed within this structure, and we can look at the relations with all other distinctions to find, for instance, that this spot here is located in a different location as this other spot, because they relate to the whole space differently. So let's skip this. So this is what IIT claims a provisional and initial explanation of the extendedness of visual space could look like. We have some properties characterized from phenomenology. We can find a translation if we find the right architecture for a plausible substrate. We can unfold a ton of other systems that have no reflexivity, no inclusion. We can model, for instance, frontal lobes more as random loops of complex connectivity that is not grid-like, and we will find that there is no extendedness there, right? So a prediction of IIT is that something like maybe olfactory cortex, since olfaction is not really extended, should not have the type of architecture that give us these properties of reflexivity, inclusion, fusion, and connection. Again, otherwise, there will be a mismatch between the phenomenology and the cause-effect structure, and IIT would be wrong. So I'm going to skip this, but if you're looking for an argument for why space needs to be specified intrinsically by grids that specify a cause-effect structure, and instead there's other areas of the brain, like I mentioned, subcortical areas that can perform the same function, but they don't contribute to consciousness, I invite you to read this paper called Of Maps and Grids that I co-authored with Andrew and Giulio, that creates, we generated two systems. One is with lateral connections and one without. They're functionally equivalent, but one is basically modeling cortex, the other one is modeling subcortical architectures, and we show that one provides a cause-effect structure, specifies a cause-effect structure that has spatial qualities, and the other one doesn't. So that's an interesting example of how IIT could explain that empirical evidence. I'm going to take maybe 5 more minutes to just say that another project that is almost completed is the one about the experience of the flow of time. And you know the drill by now. We try, this is in progress, and it's the main author will be Renzo Comulatti, who is a PhD student in Marcello Massimini's lab in Milan, and co-authored by me and also Giulio Tononi. So this time we can characterize the phenomenology of time, and we can try to infer what the neural substrate is, but we don't really know. Nobody really knows what the substrate of the mechanisms for the experience of the flow of time are, contrary to the ones for space. So we know that auditory experience, when we hear tones, we're very good at perceiving ordering, time, and duration. So there must be something about cortical, for instance, auditory cortex, that is key to understanding time within that modality. But there is time also in visual experience, of course, when we see dots appearing and disappearing, or movement or motion. So we this time took the speculative proposal that something like 1D directed grids might actually be the substrate of the experience of time. And this time the argument is a little bit like the reverse. We want to prove that if we unfold a 1D grid and we show that we can account for the phenomenology of the flow of time with a 1D grid, maybe this can ground a prediction that when we go into the brain and we look and we discover the mechanisms of the experience of time, it will be something along the lines of a 1D directed grid, which is different from the lateral connections, bidirectional connections of space. Again, what time are we talking about? We're talking about the time of experience. We're talking about the species present of William James and Husserl. We're not talking about clock time in the world. Like right now, you are hearing my words, and probably in your experience of the present, there is not one instant, there is not the last phoneme I pronounce. There are at least 2 seconds probably of words, and they are all present. And you can order moments within this window, like when you hear an ascending melody or descending melody. That's the time you want to explain. So I'm not going to go into the details of time, but this is very symmetric to what I wanted to, what I showed for space. I'm going to go on the last slide, the summary slide, which is basically the one that argues that just like we did for space, we can characterize time as this time, every moment intrinsically feels directed. It feels like it's moving away from us. When I hear a sound, like it is in my experience and it sort of fades away a little bit. So it's not like a spot solid in front of me. And it is still true, though, that moments include each other. If I hear a melody, I can focus my attention on the middle note of a triplet or the triplet itself, right? And moments also fuse and they overlap, just like in time. And we have some derived properties. So there is an interesting symmetry, but also an asymmetry between time and space. And by unfolding, in this case, the substrate, not a bidirectional 1D grid, but a directed 1D grid, we can find patterns of distinctions and relations that overlap in an asymmetric way. So in this case, you can see that in space, everything was pretty symmetric. For instance, a distinctions includes 2 distinctions in the same way, 2 smaller distinctions, but in time instead, a distinctions includes a distinction that is shifted towards the past and a distinction that is shifted towards the future in slightly different ways. And this is due to the fact that the causes and effects of a time distinctions are a little shifted. Like in a directed grid, the cause will be not perfectly overlapping with the effect, which makes a lot of sense, even given the dynamics of a directed network, right? Okay, so I hope I gave you a vague idea of how IIT tries to address the second question, which is the one of the content of experience. If you're interested, you can read the papers to get deeper in these explanations, but you can also look forward to future work where we are going to try and apply exactly the same methodology and exactly the same formalism to explain objects. So why do we see, a face instead of just seeing local qualities, color, and eventually maybe even pain? This is a painful process. It is very long. It takes a long time, and it takes also a lot of digging into the neuroscientific evidence, because clearly our substrate models are informed by what we know about the brain. But this is the methodology of IIT. We really don't see any other way around it. So I hope I give you a little overview of the core methodology of IIT, its assumptions, and the way in which it can be applied to be tested empirically by detecting consciousness, and also to explain contents of experience, making predictions based on the substrate of some contents of experience. I'm not going to talk about how to extrapolate and maybe making inferences about consciousness in artificial systems or non-human animals. We can talk about that if you want. Again, IIT starts from experience and tries to explain experience in physical terms, does not reduce consciousness to the physical, to integrated information. I hope this metaphysical foundation is clear, because I think it's the most novel, really, ingredient of IIT as a scientific theory of consciousness. It is explicit about its metaphysical foundations, and I think starting from a non-functionalist and anti-reductionist view is really key to approach the problem. I'm not saying this is the right solution, but I think it's probably an interesting direction that is worth exploring. And that is it. Thank you very much.
Thank you very much, Matteo, for this fascinating talk with so much information and complexity that somehow you managed to tame and convey to the audience. We are a bit short on time, but we have some questions, so we will start from Richard Hott. And okay. Oh.
That was a fascinating talk. Much that needs to be reviewed by me in terms of that's a lot of information. But I wonder, could you please expand on the points that were made by Paul Grasso? In other words, what's going on in the brain when people are having non-ordinary experiences?
Could you please say what kind of non-ordinary experiences?
People in deep meditation where the default mode network seems to fall away, or with psychedelics, the work done at Hopkins by Roland Griffith.
Thank you. So this is fascinating. So for psychedelics, first of all, I'm not an expert on psychedelics and neurology, but I can say what I think IIT has to say. So with psychedelics, IIT just says there is a perfectly reasonable conscious experience there, like you're having a vivid experience. The fact that you're disconnected from the environment is absolutely negligible, is irrelevant. This is also true when you're dreaming. You can be completely disconnected, but having a vivid experience. So it is an internalist theory in the sense that experience is really sort of specified, generated from within. So psychedelics might also constitute an interesting case to test IIT and also to test whether the level of consciousness is higher in altered states of consciousness or lower. So, for instance, applying PCI, it could very well turn out to be the case that psychedelics increase integrated information in the brain because there are much more relations between the distinctions that are specified. And phenomenologically, this also makes a lot of sense because there's new insights about the connections of different concepts. For instance, when we see a piece of art and or we just look at a wall and you see a lot of things on this wall, or we feel a lot of emotions and connect the meaning of different contents of experience on psychedelics, this should be addressed also with the formalism of IIT. For deep meditation, IIT is one of the few theories that actually argues that, again, it doesn't have to be that the brain is very active to have consciousness. There could even be mostly off neurons that are not firing, but as long as their cause-effect power is there, meaning they could fire if they were stimulated, the prediction of IIT is that will support an experience. And this is actually being tested in one of the adversarial collaborations between IIT and predictive processing or active inference. So I invite everybody to keep an eye on the results because this has been experimentally put to test in one of these adversarial World Charity Templeton Foundation adversarial collaborations. So thank you for the question. Very interesting.
Thank you, Richard. So Trevor now, and Matteo, maybe to give everyone a chance to ask their question, if we can all try to keep questions and answer as short as possible. Sorry about that.
No.
Yeah. Hi. Thank you very much. So IIT is basically, it has the axioms about phenomenology, and then you're assuming a substrate. So I myself have a medical background, but then moved off into looking at emotional processing and consciousness and in social groups. And I'm interested in what some people call psi phenomena, things that don't fit the normal space-time frame, like dreams that foretell the future, and things like this. Now, the theory that I'm coming up with is that the brain is actually evolved to directly engage with the quantum substratum behind what we consider is biochemistry, biophysics, or whatever. It's a very deep engagement in hollow movement processing at a quantum level. Now, the axioms that you've got, I can understand why you focused on the brain, and it's got very practical applications for people who are, are they alive or dead? But could those axioms just be transferred onto assuming that the quantum substratum is the substrate of consciousness, which goes beyond the body? But I mean, every single neuron is emerging from that quantum substratum, just as social groups that we interact with and people that, you bring in love here, people who remotely from you, there is a bond of love, can have remote knowledge of each other, because maybe the substratum of consciousness is actually at that different level, beyond the body, beyond materialism as such. But what do you think about the application of the axioms to other substrates?
Thanks. Very interesting question. So I would say that IIT does not exclude that possibility in principle. IIT, if anything, provides the tools to test that hypothesis. So IIT claims that the substrate of consciousness is wherever integrated information is maximal.
Yeah.
If it turned out, if we were able to compute integrated information, looking at some quantum, mechanisms that extend from our brain to our surroundings, and integrated information was maximal at that scale, then IIT would say we have no reason to say no. That it's absolutely not committed to the fact that the brain is, the system. Yeah. And the point is that we have a lot of evidence, of course, from neurology and neurophysiology that tells us that probably posterior areas of the brain are more responsible for consciousness, the time scale of neural firing, and people disagree with this. I invite you to check. So first of all, Christoph Koch, who is an advocate of IIT, is a little more strict and says, no, quantum phenomena are completely out of the picture because the brain is too wet and hot and big, and that just doesn't make sense. So you have one camp. The other camp, however, is there is an interesting paper by Larissa Bantakis on quantum IIT. You can compute integrated information in quantum systems. The question is whether the brain is a quantum system and consciousness emerges, or consciousness is specified at that level. One more thing, just there is another adversarial corroboration that is being established between Stuart Ameroff and Giulio and our lab. And this is also another interesting way to sit down and ask, okay, can we design an experiment where we actually make predictions based on or some quantum consciousness theory and IIT and see where things go? So this is open, but thanks for the question.
Thank you so much. I'm very aware, and I would actually like to email you afterwards about that with Ameroff. But just simply, your composition axiom would simply be reversed, because you simply say that the brain is putting in an informational source into a wider substrate, and you're just reversing the process. Anyway, look, I've taken enough time. Thank you very much for your response. Yeah.
Thank you. Anton Arkhipov is another researcher from the Allen Institute who published interesting papers on quantum IIT. So please check it out or email me and I'll send a reference.
Thank you very much, Trevor. And now we have a question from Peter.
Thank you, Matteo, for the great presentation. One of the things that you didn't say very much about was phi. And it's sort of come into a fair bit of criticism, because if all the information is intrinsic, then it's computationally explosive. It's relatively unconstrained, whereas in predictive processing models and active inference and things, it's much more constrained. Do you see that as a problem in IIT?
I see it as a problem every day, because I try to unfold little systems and I have constraints, like I can't unfold more than 20, 30 units, right? But let me say one thing. So it is pretty normal in neuroscience to make approximations and macro, systems like the brain in areas. For instance, we can consider one entire node being the occipital cortex and one node being the thalamus, and we can then correlate. So IIT, in principle, measures of phi can be applied to macro version of very complex systems. In my work, specifically working on the simple neural networks, wants to compute phi exhaustively. So every distinction, every relation is computed. But there are, of course, approximations that we can design, both from mathematical analytical solutions or just like shortcuts that can then be applied to bigger systems, such as the brain. And PCI is the opposite spectrum. PCI is a very crude, not even approximation of phi. Is, if anything, it's a measure that can correlate with phi, can say something about integrating information. But the thing that I want to stress is that a measure of consciousness, it better be explosive, because consciousness is incredibly rich. When we look at the visual field, for instance, all those little spots, it's mind-blowing the fact that in the fingernail that you hold in front of your eyes, there is a grid of probably 3,600 little pixels that you can only in your fovea you can resolve. And if you extend it to the visual field, it means that you must have billions and billions of mechanisms that are just contributing to bits of darkness of black in your visual field. So imagine how many more mechanisms there are that are contributing to all the rest of your experience. So I am afraid consciousness is complex, and therefore the computational explosion is just, it's a feature. We are capturing something that is real instead of basically oversimplifying and missing the real objective that we have in front of our eyes. Although methodologically, I agree with you, it's an obstacle. So thanks for pointing that out. I'm just saying, I'm happy to stick around a little more if anybody wants to, if you don't have a hard stop. So
actually, Matteo, we ran out of time. I'm very sorry. Perhaps if Joy has a question, can maybe send you an email, maybe?
Please, absolutely, yes.
And I would like just very briefly to thank everyone for participating to this series. It was, for me, it was a great honor and a pleasure to be to host this series. I would like to thank Alex Gomez-Marin. I would like to thank the Paris Center, all the speakers, of course, you for coming and making this possible. And please send feedbacks if you have any feedback on the series. You can mail me. And from my perspective, this has been a success, both in terms of number, in quantity and quality, to stick to the theme of the series. And so perhaps we could think about organizing a sort of sequel to this series. So if you are interested, please let us know, and let us know what we can do better and what we can improve. For myself, I can definitely try to improve to stick to the schedule. So sorry for keep you longer, but it was a pleasure and an honor to share this experience with you all. Thank you very much.
Thank you, Francesco. Thank you, Matteo, for today. Thank you, Alex and Francesco, for organizing the series. And thank you all for participating and being here with us. And we look forward to seeing you here again at the Paris Center. Bye-bye, everybody.